really excited to be, introducing Sherry, our guest speaker today. So Sherry is a first-year faculty in the HCI department, but she actually does research at the intersection of HCI and NLP. And she's worked on things related to helping humans, studying how humans interact with AI systems, and so that is both users, sort of lay users, as well as experts like y'all in the room, and helping debug NLP models and AI models in general. She's done really cool work in rationales and studying how rationales can help with model interpretability. And she's also, notably, has gotten a Best Paper Award at ACL 2 years ago for her work on checklists, and also an honorable mention at Chi on some really cool work on mitigating and sort of studying gender biases in greeting cards. And Sherry and I actually did our PhD together at the University of Washington, and we just both moved here, which is really exciting. So without further ado, you go ahead.
Thank you. Thank you, everyone. Thank you, everyone. Sorry we took a little while to figure out the tag. Both Martin and I were new, so we didn't really know our way around. We were a little bit late. But thank you so much for being here, and I'm super happy to kick off this series of Colloquium for this semester. And like Martin already mentioned, I actually just moved to CMU. This is my second day of my official new work. So I'll just take this chance to do a self-intro and talk about some of the work I did during my PhD, so you will get an idea of like, oh, this is what this affiliated faculty in that other department is doing, basically. Okay, so the title of my work is called Interactive AI Model Debugging and Correction. And so let's start with this buzzword AI in the title. So my whole line of research pretty much started as I see AI systems really trying to help us everywhere in our lives. They help us on everyday tasks like setting up our alarm clocks, they write code with us, and some of them even drive our cars. But I quickly realized that as these models try to help us, they actually also make us to face a lot of their errors. And some of these errors are pretty hilarious. Like here on the left, I want to get up at 6:30, and Siri says, OK, I will wake you at 6 a.m. And it actually sets my alarm at 7. So I have this 1 hour buffer in between that I don't really know what I'm doing. And some of the errors are much more fatal, and I would definitely not want to be in a car accident, maybe caused by Tesla. Apparently, we don't want these kind of errors. So what do? Well, we try to create better models that can make less mistakes, and better here is usually measured by some standard metrics like maybe higher accuracy or higher F1 score. And we have improved a lot. If you see this chart, this is basically a line chart tracking our progress on improving model accuracy, and each shape represents a different kind of NLP task. And the blue dotted line is the average model performance across all of the different tasks, and the black line is the average human performance. So many models now are performing better than our human baseline, especially on some standard data sets. But unfortunately, this is not going to be enough. And why is that? Let's think about this by teasing Google Translation. So even in 2016, which is when I started my PhD a long time ago, Google Translation was said to be quite good. Yes, it got a lot of questions or a lot of inputs correct quite decently. And here, we're translating from Chinese to English. And the model is actually correct in both languages. It's saying Android system is pretty lagging. But if we just modify this Chinese input a little bit by switching this Chinese word pretty with this close synonym very, then it starts to think Android system is really fast. Yay, Android system. But this funny example is telling us that when we see a model being correct on maybe some examples or having a really high accuracy score, it's usually really far from enough because the model could be right for the wrong reason. And if, for example, they're relying on the wrong features, then maybe you can just do a small tweak on your input, and it will just mess your model up. And some of this could also represent something even bigger, like maybe the model just always gets something is pretty blah correct and will always mess up on something is very blah. Or in other words, it's definitely possible for us to have a model that is having flying scores, but it will just break if we use it on certain kind of input or certain kind of use cases. When we see this kind of error in deployment, there's very little we can do. Maybe we can tweet about it and tease about it on Twitter, and that's in itself a big problem. But if we end up in this stage, it usually also means we did something wrong during the model development. So what's in this gray box? Let's unpack this a little bit. And when we develop a model, the very first thing we try to do is to collect and curate some training data. And this data becomes the basis of our model, but it's usually not very good or not good enough to represent the world we're in. If we're not careful, then maybe this very lagging version is just never really in the data set, so there's no way for us to know how our model would behave in the real world on those cases, which causes this mismatch between the accurate model and the actual successful model that we mentioned before. Then we train a model, and then we move to evaluate it. Here again, we tend to rely on a lot of standard metrics like accuracy, but in fact, accuracy is also not a very good representation of what we would expect from the models. So we expect the model to do like correct reasoning, but we only get to figure out that our model is doing incorrect reasoning. In the translation model, if we actually come in and look at these two examples and realize, oh, they're so similar that they should be treated as a pair, and they should behave in one way or another. But when we just look at a single accuracy, then this error is just treated the same way as any other errors that we may or may not care about. And so they will just decrease this particular accuracy score by a little bit, and we don't really get the rich information that we are getting through the comparison. OK, let's stare at the slides for a little bit, and then shift our attention. Essentially, what's missing everywhere is humans. We're not really considering all of the use cases from humans, and we are also not considering all of the expectations from humans. But we, as humans, we are really important. And our community is getting more and more aware of this fact that AI technology is made by people, and it's also going to be used for people. So human is the gap here, and this gap pretty much motivates all of my work during the PhD. I work at the intersection of human-computer interaction and natural language processing, and I try to design frameworks and tools that can help people interactively debug and also correct their AI models. So some of my work are used by AI experts to validate the system before we actually deploy it into the wild. And some of them are designed to be used by end users as they try to collaborate with AIs on their own tasks after the model is deployed. Back to the three problems we saw earlier in the translation example, I tried to tackle each of them and eventually arrive at a roadmap of three main themes. And so for evaluation, where people's expectations are usually overlooked, I try to build some frameworks and tools to help experts express their expectations on the AI as they evaluate the model. Erudite and checklist are cute names for my projects, and I'll get to them later. Second, in data collection, I built some NLP models that can augment experts on collecting how humans would use the AI. And finally, for end users with deployed models, I designed some interaction technologies to help those people recover from the error they see as they collaborate with the AI. I'm happy to chat about any of these projects offline, but here I will just talk about three representative projects from each of these colors and try to dive in a little bit. So please remember this outline, because I will come back to it again and again as a tracker for the talk. So now I will first get to Erudite and talk about how I help experts express their domain knowledge and do the analysis. Back to these two problems we saw earlier. Model analysis is our way of revealing model deficiencies that's not really reflected by accuracy scores. We analyze models to find data groups or data slices that the model cannot really handle, and also to find when the model is relying on some irrelevant features. Experts, people like you, have a lot of really applicable knowledge in this space. They know where to look, and they also can really easily judge what features are relevant or irrelevant. But something really fascinating about text data is even though text is really understandable for humans, it's actually really complicated for machines, and it's very unstructured for us to do any kind of formal analysis. So what's the workaround? If we read either some dataset description or some modal error analysis sections in the NLP papers, they all have this shared universal method. And really, it's just different ways of saying, oh, let's take a random sample of the data, manually categorize them based on what we think are the important or similarities or differences. And this is a pattern we probably will never see if we're playing more with the structured data, like a spreadsheet, where you can just say, let's do a group by on this particular column, and then we can call it a day. So this pattern really intrigues me and makes me want to ask, how can I help experts fully utilize their expertise in modal analysis? Which leads to Erudite. So through Erudite, I find that the state-of-the-art random sampling approach is just really unstable and also unreliable. And so instead, we should really rely on two different building blocks. First, we should do systematic grouping of relevant examples so we can more confidently understand when would the model fail on what kind of examples. And second, we should do counterfactual rewriting to test and isolate the impact of irrelevant features. And I will explain this in the next several slides. And I will do the explanations through a walkthrough case. So in Erudite, we built this interactive interface for making the two building blocks really easy to use. And it looks something like this. And I will show you how I would use this UI to analyze a visual question answering model, which is basically trying to answer questions on images. So when I load the model and the validation data into the interface, the first thing I usually do is to go and check on some of the individual instances to get a sense of what the model tends to do. So let's zoom into these two examples. They're both doing counting. The ground truth answer are both 3. And the model gets how many people correctly at the top, but it will miss how many yellowish donuts in the bottom. What's your first impression on these two examples? Well, mine is, my model does not really know how to answer what-if questions followed by an adjective. Now, I want to know if this is a really generalizable observation and whether I can maybe report this problem in a paper and then share it with the community. So what do I do? If I follow the status quo I mentioned earlier, then it's actually pretty simple. I would just count the number of how many adjective errors. I would maybe report 5 out of 100 in my paper, which actually doesn't seem like a lot. But this 100 sample data is just such a small portion of maybe the 100K validation examples that I actually have. So I'm not quite confident that I have looked at enough examples or I have covered enough things. So instead, I would really hope there is a way to scale up my observation beyond just this random spot check. And this is where our first building block of grouping comes in. To make sure experts can build the data group they want, I designed this domain-specific language, or DSL in short, which try to help people to easily define what kind of attributes they would want to extract from some text instances. This can go from really simple ones like how long is your sentence to more finer-grained ones like if the sentence includes a short phrase like adjective plus noun. And then in this filtering panel in the interface, let's zoom in a little bit, we can write queries on the right attributes to find the right instances. Back to our example, on this how many people case, Erudite will try to do some programming by demonstration trick and suggest some possible future queries. So I can select from them and maybe use how many noun to find the similar instances. Similarly, for the how many yellowish question, we can generalize it into how many adjectives. And then with these filters, I can build some data groups in this interface, which can help me find about 10K examples in how many noun questions, and another 700 or 800 how many adjective questions from the validation set. If I further look at this orange bars, then I can see indeed the model performance is kind of different on the two groups, it has a much higher error rate of 63% on how many adjectives compared to maybe only 39, well, not only, but lower, like 39% in how many now. But because this how many adjective group is just so much smaller, I don't really notice this when I just look at the overall model performance, or maybe when I only sample some errors to look at. And so now I can report with some more confidence that maybe my model cannot really count objects with adjectives for 60% of the time. So grouping is good because it helps us compare data slices that we might have missed otherwise. But when I report this in this widely used text description format, do readers actually know what they mean? So we asked several NLP experts to translate how they think about this kind of text descriptions back to the DSL in Erudite. And we realized, no, the experts would make really wild and different interpretations. Some people would do what I did and search for questions that start with how many adjectives. Other people would say it counts as long as there is an adjective in my question sentence, no matter where it is. And by asking people to really explicitly write out these groups, we can find the differences in their analysis, like here, white is at the end of the question, so it doesn't really count for my group, but it can count for someone else's group. And because Erudite queries are precise and also reproducible, it also makes the analysis much more reproducible. But it's still not enough. I still don't really know if the adjective in the sentence is the root cause of all of these mistakes. And so here comes the second building block, which we call counterfactual rewriting or counterfactual analysis. It's basically a set of tests on what could have happened or a set of examples for answering what-if questions. In this particular example, I want to ask if the adjective was not there, would the model predict correctly? And I can inform Erudite of my what-if question by deleting this adjective and changing it to how many donuts. And now the model can make a correct answer and say there are 12 donuts in total, so seems like I am correct on this very particular case. And Erudite will also try to express my what-if question with rewrite rules, again in the domain-specific language format. So I can keep the last rule and move on and reapply the same change to a larger number of instances and quantify the impact of adjective as go. Like here, I can choose to remove orange on this cat question. And obviously, this kind of change also affect the ground truth answer, but we can still learn something important even though we don't really know the new ground truth answer. So in this case, the model is saying there's only one cat, and if I compare it to the original prediction, then I know my model really does not know how to do counting, because otherwise it should definitely count more cats than the orange cats. So in this way, counterfactual analysis help us find cases where the model is correct, but for the wrong reason. And we can do this without knowing the new ground truth answer or new ground truth label on the generated counterfactual examples. And with this rewrite rule and also the expectation combined, they can form a counterfactual test on whether the model knows adjectives, and we can get a score for how frequent the model is being inconsistent. And this idea kind of also inspired me and my collaborator to write another full paper on testing model capabilities. I will not get into that paper, but basically, if you create different kind of specific tests on different model capabilities, and if you also test these capabilities in different ways, then you can get a pretty nuanced performance metrics on what the model can and cannot do. And it will greatly expand beyond this one accuracy score we usually use. And it also expands beyond the data that we have at hand, because we are constantly creating new comparing or contrasting examples. Erudite and Checklist has moved on to make some practical impact in the field. We've seen researchers adopting Erudite to their own models, and here's a sample of a relation extraction paper. And we've also worked with people at Paper with Code to embed checklists into their default leaderboard and help people to compare the nuanced model capabilities. So hopefully I've convinced you that grouping and counterfactual analysis are both very important and help experts do them through the erudite domain-specific language and also the interface. And by helping experts express their expectations on the models, we can encourage more reproducible, scalable, and also testable analysis. Erudite is the demo case for expressing expert knowledge, but it's actually also the grounding of many of my other work as well, in a sense that grouping and also counterfactuals are useful not just for error analysis. They're actually necessary for a lot of other development stages as well. And so now, instead of error analysis, let's think about what we need to do when we do data augmentation. This is now almost common sense, I guess, but naturally collected data sets are not good. They have different kind of problems or gaps in their distributions. But if we can do different kind of counterfactual rewriting on the data set, then we can add a lot of more signal in the model training. And this is hopefully a pretty promising direction because this is hinting that after we do the analysis, it is possible to fix the model by fixing the data, or at least to some extent. But in this case, we really want to learn something that's just within the data or within the model. So our own belief can actually end up biasing us. And so we want to compensate for what experts might have missed. And so here comes my second line of work. I try to build some NLP models that can help augment experts. And I will explain how I augment experts on counterfactual rewriting with the second project called Polyjuice. And as we will see, this is in fact useful for both the analysis and the augmentation. So Polyjuice mostly emerged from how hard it is for humans to create counterfactual rewriting or to do counterfactual analysis. We're really biased and we have pretty limited creativity. For example, in our previous VQA case, to understand this impact of adjective, I really easily just removed yellowish. But I miss all these other useful changes like, can we test a different adjective, or can we change the syntactic structure entirely and then ask how many kinds of donuts? If I really think hard enough, I might be able to get them, but I would just waste a lot of time, so I usually don't want to bother. And so here I ask, how can we collect more diverse counterfactuals that compensate for what humans have missed with less cost? Because language models, you don't know, it's a family of NLP models trained on really huge amount of text. They see and remember much more data than we as humans ever could. We want an automated generator that can help us fill in a gap, and that's how we started Polyjuice. At a really high level, we basically fine-tune this language model, GPT-2, and then try to basically, given an original sentence, Polyjuice can make some closed counterfactual rewrites. We want Polyjuice to generate a bunch of changes per text to get some diversity. And so I try to put in some signal to drive different kinds of how and also where to preserve and rewrite. For example, how to change would rely on a list of control codes. Negation here might give us how many donuts are not yellowish or how many non-yellowish donuts are there, versus insert might just help us add some constraints and say the donut also needs to be sprinkled. As for where to change, we rely on this fill-in-the-blank structure. So by replacing yellowish with blank, we're telling the model, please only fill in this part, and the model will generate things like colored or yellow. So this new counterfactual could be like how many colored donuts are there. It might also just delete this particular part and give us how many donuts. So this Polyjuice actually helped us. We did a user study with 13 graduate students, and basically, given each individual original instance and also the prediction, the students can play with the model and do some manual counterfactual analysis up to 10 times. And then they were asked to guess what the predictor would do on some Polyjuice-generated examples. We saw the students basically really couldn't do the simulation. This means the generated examples go somewhere that's beyond what they have already tested in their own analysis, and they actually supply more information. And we try to analyze what's missed by the students, and the examples actually demonstrate the two reasons quite nicely. And the first one is people just tend to do their own inspection, or like overfit to their own inspection. So after they have already seen the model being run on how many yellowish donuts and also how many sprinkled donuts, they would just incorrectly generalize their observation and think, oh, the model will just always be wrong, whatever kind of adjective I have there. And then they would miss the case where the model can actually answer how many yellow donuts correctly. The second is for 85% of the time, people really just prefer to do something locally. And this means they will not really think about, for example, moving the adjective around, and they wouldn't know. In those two cases, the model can also be correct. And with this in mind, if you still remember our earlier hypothesis, hopefully this polyjuice result help you get some refreshed view that maybe it really depends on what the adjective is in the question and where they are. So this way, polyjuice diversity help us do some more in-depth analysis. But like I mentioned earlier, polyjuice can also help fix the models through counterfactual data augmentation. So instead of asking VQA models to do predictions, we manually crowdsource and label a diverse set of rewrites. For example, we can move the adjective to say the adjective location does not really matter, and change yellowish to say, wait, but the actual adjective does matter. And if you're asking for sprinkle things, then the label would be different. And then the object obviously also matters. We can add these generated examples to the original sparse data set. And with the label, we can now train with this polyjuice counterfactuals. We did 3 tasks in our paper, and I'll just show a subset of the result here. And so compared to just adding the same amount of original data, polyjuice increases generalization to some out-of-domain data set without really decreasing in-domain accuracy. So here the original is trained on SST2 data set, so it's the sentiment analysis data set on movie review sentences collected from somewhere. And then the model trained with polyjuice augmentation performed better on the Twitter sentiment analysis data set, and it also did better on some manually created IMDb counterfactual data from some previous papers. So counterfactual data is pretty useful. And compared to adding the same amount of human-created counterfactuals, polyjuice got compatible or even better results, but we do it in a way that's more effective in terms of labeling time, because people only need to verify the counterfactuals created by polyjuice rather than creating them from scratch. So polyjuice is also more effective. Polyjuice, together with some other great work from some other great groups, I think successfully started to attract the NLP field to really consider this theme of perturbation or counterfactual-based augmentation. Polyjuice once received more than 20K downloads on Hugging Face per month, and some of us also came together and created this challenge called NL Augmenter. And we got, I think, 20 experts to contribute some creative counterfactual strategies. I'm just excited to see people using a lot of different sources like language model and others to do this thing. So here the big picture is with polyjuice as a counterfactual generator, I got to augment experts on counterfactual analysis and also model improvement with the context or information we already have in language models. We augment experts both by increasing the diversity to cover what they would have missed, and also by reducing their task time. So after this, I will switch to a different walkthrough example, and this will be a good chance to ask questions if you have any burning questions at mind.
I might list this about the counterfactual data augmentation thing. How do you get like the label in the counterfactual?
We basically just put it on mTurk and ask crowd labelers to label them. And the thing about that is because the counterfactual examples are close to each other and also to the original example, you can actually ask crowd labelers to label them in a group. And so people only need to read the change part to determine, oh, should the label be affected by this? And it actually reduces the labeling time per instance.
Thank you for presenting the very impressive work. So far, I've seen a lot of examples motivated by linguistic features.
Yeah.
I was wondering if these frameworks can be more can be like easily extended to like other types of errors, like the types of errors that the models might make as like the models progress. For example, like in future we might have models that do better on linguistic aspects, but there might still be some domains that are out of the model's reach. For example, like different styles, different like socioeconomic background of the speaker, for example. Yeah, these frameworks examples.
That's a great question. Actually, like, sorry to pause. Do I need to repeat the question for recording?
That's okay.
Cool. So the question is basically, most of the examples and the use cases I presented here are more motivated by linguistic-based errors, and is this framework extendable to things that's more advanced, different kinds of errors? So when the model get better on syntactic stuff and linguistic stuff, can we still use the framework to test the model on like semantic things or styles or some other things that we care about in NLP? And that's a really good question. So there's some echo. I don't know. Maybe other people can mute. So yes, I agree. So it's sort of because of the timing of those projects, somehow we just focused a lot more on the syntactic stuff. We had some work. One of them is called Taylor. It's out 2022 in collaboration with AI2 people, and we try to extend this counterfactual thing more onto the semantic style. Like, for example, we would try to use the semantic role labeling kind of labels as the control signals to change some semantic information in the sentences, like who is doing what at where, so that you can use that kind of information to create some more practical counterfactuals. For example, we could have a sentence, Sherry is having lunch, and another sentence, Sherry is doing presentation. Those two events maybe should be conflicting with each other, and that could be something that can test model in some more like temporal information or like common sense use cases. So generally, it's extendable, and also for I guess it's also worth mentioning for some of the more generative models, it's also like the checklist kind of framework we think it's also possible to use there. And basically, it's a matter of creating the right test cases and the right expectation. For example, for a translation model, maybe your expectation is before and after the translation, the entity names should still have the same relation with each other, like from the semantic role labeling kind of perspective, the subject should still be the subject, the object should be the object. They shouldn't have this reversed relation in the new sentence, and those kind of really nuanced expectations, if you implement them right, it could help you test a lot of different models.
Also a question about the counterfactual data.
Yeah.
I was wondering, I know you're studying maybe if this is more like particularly for the community task, but there might be some questions that are not answerable. So, for example, the example you showed, like how many donuts, like donuts, for example. What if we change the question to how many donuts are outside the box? So from the image inside the picture, you cannot answer the question. Whether you were trying.
Yeah, that's also a great question. The question is, when you create counterfactual examples, there could be examples that just fall out of the general distribution that you're creating. Like maybe they do not really understand the context of the image in VQA. So like if you create example like how many donuts are outside the box, then basically it's not answerable. And is it worth of adding that to the data set? What does it even mean? So for question answering, like I don't really know what's the status of VQA right now, but at least for question answering, there's this one particular group that's just not answerable question, and those questions also help to tune the model so that when it really cannot answer it, it shouldn't hallucinate some kind of answer. So I think it will be valuable in that sense, but it is a limitation of PolyJuice that it's harder to really embed in this particular context you want to have in your counterfactual rewriting. And so in Taylor, that other paper in ASL 2022 that I was talking about a minute ago, we also try to have some kind of more keyword-based contact information. So basically, for a QA task, you can try to extract some information from your paragraph and say, I need this information to be in my new question, and then so that your new question will not be too far off from the paragraph that you're playing with. Cool, then we can move on, and then if people still have questions, we can answer them later. Okay, coming back to our really big workflow, besides polyjuice and erudite, I also have some other work for some other development stages that I will just not talk about, but we do cover many things from analysis to fixing. So let's assume we're now ready to deploy some models to end users. Unfortunately, these models will still make mistakes. They will just never be perfect. It's just part of the definition of AI models. And so when end users face these models, they know what they want from that model. They also know when the model is not doing what they want, but they don't really know how to deal with those errors. And so my goal here is really just to use the interaction to help users deal with the errors. And as an example, I would talk a small series of work on how I design unique interactions to support end users interpreting and also controlling large language models. So since 2020, our NLP community has deployed this so-called large language model. And what's impressive about them is their ability to respond to some arbitrary natural language prompts at runtime. For example, if I want to do English to French translation, I don't really need to train a separate translation engine, but we can just fit into the model something like, given this English sentence, translate it to French, and then the English sentence, and then denote the starting point of the French sentence, and then the model can just continue this prompt with this French translation. But users really want to do more things than translation. When I was working on this project, many of our users, this was my Google internship project, so many of the users were like Google employees who have access to this model but really don't understand what the model is doing. And they just really want to use this same large language model for rewriting their short summaries into some friendly and constructive peer review paragraphs. And their short summaries sometimes look like this. Sherry could improve her presentation skills. She has too much text on her slides. Her presentation wanders from topic to topic without a clear structure. She also does not really engage with her audience when she presents. And the model indeed can do the rewriting. It generates something for them. But this generation really doesn't match with their expectation. So you can pretty clearly see this paragraph is still kind of mediocre. It's just mostly impersonal and does not really give you concrete suggestions. For example, it just says you should have a clear structure in response to without a clear structure. And if I got this feedback, I would be like, well, what should I do? One second. OK. Now, if you work on NLP, which most of you do, or like if you more specifically work on text generators, then you can guess what went wrong. Basically, there are some limitations in the modeling structure. The model doesn't really know how to do reasoning, and they start to get biased by their own generations as the text become longer and longer, et cetera. If you don't work on these, don't worry, because end users also don't really know what I'm talking about. But they're the users of these models. So I need to answer this question: how can I help end users interpret and improve model outputs when they don't really understand the underlying structure and also really cannot change the model at all? And my way of doing that is to build this kind of AI chains. I try to provide some more explicit knobs to end users by breaking down an original task into some subtasks. What's the intuition behind this? If we really think about many, many tasks similar to rewriting, the problem from the end user perspective is just because the task has a lot of things going on, it's really hard to build this input to output mapping. It's not really clear how the users can help the model know what kind of presentation problems exist and also brainstorm suggestions and also do rewriting. But this mapping does exist if we just make the task smaller and also more targeted. So instead of rewriting a full paragraph, if we just ask for suggestions on a single problem that does not engage, then we get pretty explicit suggestions like ask the audience questions, walk around the room, And then end user can come in and say, I don't like this because some of my talk are still virtual. And so I want to keep iterating on it until I'm happy and maybe get things like use humor. And then if we pass this human fixed suggestion to another large language model that really specifically focus on just rewriting suggestion bullet points into friendly paragraphs, then we get a much better paragraph like here. You may want to ask more questions to engage the audience, and humor always helps. So packing them together, we have a chain. We ask large language models to complete each subtask separately and use the output of one step as the input to the next. So the final result will just aggregate all of the results from the previous steps. Our peer review rewriting task can be completed in these 3 steps. And I also built an interface for users to actually play with this chain. So pretending you're the peer review writer right now, here's how you're going to work with this chain. So in the interface, we will use this visual flow to track the underlying structure of what large language model steps are involved and how the data are transformed. So getting into the first step, given the original feedback, we asked the model to split it into a list of separate presentation problems. The problem is really similar to what we saw before, though we make it look a little bit more structured in the interface so people can play with them. Then we take the output, this problem list, and move to the second step and ask large language model to ideate suggestions per problem. So here we can run the model on too much text independent of other problems and get suggestions like use more graphics, and we can refine them. And when we're ready, we can move to the next problem of minder from topic to topic. Then we can use both the problems and also the suggestions as the input in the third step, so we can compose our final paragraph. Now this rewriting is much better. If you can read this green paragraph on the far left, basically it has like phrases like, oh, your presentation was so interesting, and also some good suggestions like it might be helpful to vary picture with text, and if it were me, I would divide it into sections. If you think about this, this is pretty amazing. Arguably, in all of these 3 steps, we're just asking this nice language model to do something pretty simple. So in a way, we're just repeatedly underutilizing what the model probably can do. But just by doing this, the final result is also better. So it's saying for these models, sometimes less is more. Through a user study comparing chaining to just the standard baseline without chaining, we see our users really liked interacting with large language models through chaining. In particular, they find chaining making their interaction with large language models more transparent, because after this task decomposition, users are more aware of what the things the model can do. For example, one participant said chaining helped you speak the language. It lifted the hood and showed what's happening at different phrases. They also feel the interaction, like interacting and also the changing the output of each step really helped them to steer the model towards their final goal. One participant phrased it like this, and I liked it. They said chaining makes it easier to fine-tune things. And fine-tune obviously means something else than what we mean in NLP. So they really don't really know what like the NLP context is. But basically, too much freedom without chaining is a curse. One more interesting thing in the chaining project is I think this really perceived transparency and controllability really made users more comfortable and also confident when they interact with large language models. So beyond just completing complex tasks, some of the UX designers in our user studies discovered by themselves that they can use the same chaining idea to prototype some really complex applications. And this is an example chain built by one of our UX designers for prototyping a music recommendation chatbot. Basically, it just has several branching logics to like detect and handle different kind of queries people submit. Like for example, if you say, play music by the Beatles, then the chatbot will try to outsource this music query to YouTube API. Or if you say something really unrelated to music, then it will try to chat with you and ask what it can do for you. The designer was pretty excited because they couldn't figure out how to design the instruction to make one large language model to do all of these. But they can build this really multi-step chain in just a few hours. And I'm also excited because I can see training being the bridge between large language model and end users. So AI training helps end users fix large language model errors by giving them explicit knobs that they can tune on some subtasks. And that concludes the 3 examples I wanted to cover. And this whole line of research have been making some practical impact in both the academia and in industry, again, with the community really analyzing insights and sharing knowledge with these tools. And some of the tools have also been or will be integrated in some open source AI libraries or deployed internally in industries, which is pretty exciting. And eventually, all of the work is trying to give a way in for people to evaluate and interact with AI systems based on human expectations and their needs and their goals. I also have some other ongoing collaboration right now that goes a little bit from a different angle. So instead of humans having to really explicitly say, like, define what they need, AI models can also get a little bit more proactive in the process. For example, when we do in-context learning with large language models, our own demonstrative examples can under specify how we expect the model to behave on different kind of inputs. And we can do something really similar to active learning. And so large language model could give us some input that it is not sure about, and then they can use our feedback to build maybe better in-context learning functions and behave better. Or we can also try to broaden the definition of explanation, like XAI, not just to explain a single model prediction, but actually try to explain how people would use those predictions. So we had this work. It's in collaboration with people at Penn State using some NLP models to help people write better paper abstracts. So it's something I'm sure many of you would want. And one assistive model we were using was this classifier that predicts writing structure of your abstract. So it's saying this sentence you're writing seems to be describing a method, that sentence is describing maybe your finding, your contribution. So if the classifier says, for example, your last sentence in the abstract seems to be providing some background knowledge on your work, then it doesn't really, the explainer wouldn't just say, oh, this, I think it's about background because of this several words that's important for the prediction. But it will say things like, based on the distribution of, for example, abstracts in top NLP conferences, the last sentence should maybe be the contribution. And maybe you can perturb this sentence in this particular way so that it's actually describing the contribution. So in this way, the explanation is really proactively helping us to answer, what do I do when the model is giving me something that I didn't anticipate? And it's helping people to achieve the goal of improving their abstract. This is a very small screenshot, I know, sorry. But it's a paper we're planning to submit to Kai in 2 weeks. So if you're interested in trying it out, let me know. I'm pretty sure we would love to have more testing uses. Eventually, all these work serve this higher goal of trying to design, evaluate, build, and also interact with AI systems that are compatible with human goals. And under this huge umbrella, going forward, some questions I think would be worth keep answering would be, first, how are people using AIs in practice? So with the data being the primary communication channel we have with AI systems, can we try to recover human needs from the data they submit to an AI system and say, for example, people who code together with big models like Copilot, maybe they use it more to complete a maybe less than 3-line code snippet rather than completing an entire Python function from the beginning. And second, after we know what the users care about, how do we evaluate and also know AIs are beneficial in those cases? How do we measure things like partial gains? For example, when people think the AI-generated code is fair enough that they would be happy to accept it, but then make a lot of changes on it, how do we measure like it's not when the correctness is not 0 and 1? And finally, when we know what it means for a model to be beneficial, can we use human feedback to make the model more beneficial? And what are some best ways to collect those kind of human feedback? I hope to keep working on this in my next several years at CMU. I'm pretty nearby, just in that less fancy building compared to Gates. It's called New Simon's Hall. So if you're interested in this stuff or just human AI interaction in general, feel free to come find me. And with that, I'm happy to take more questions.
For like the end user interaction part, what do you think about the adversarial users who are make bad examples or make bad input to the system?
Yeah, I think it kind of depends on like what is that bad input going to be used. Like if people are just going to tweet it on like Twitter or something, I think the state of the art right now is basically if the model is prone to give you something that would be bad for the society or be bad for even just a PR, it basically will just have warning messages at this point. But I think if there are enough people playing with the system, some people in benign way, some people in adversarial way, eventually they naturally form different kind of data slices, and those adversarial ones should be detectable based on like similarities with some other examples. And from the model deployer perspective, they should be able to block it to some extent, but that will take extensive effort, I think. That's a great question. Oh, and the question was for end users, what do we do if these users are adversarial and asking questions that basically are attacking the model or for some bad use?
So particularly in the first half, unless I'm misunderstanding,
yeah.
The way that these examples or these patterns get extracted is based off of the service forms, and in the sense that like there's something like yellow that is predicting correctly. But we also, like, there's the interpretability literature on like integrated gradients and other stuff like this, like attribution, which would theoretically tell us maybe what part of the input was most contributing to a prediction. So is there a path forward here where you leverage something like that to basically guide the construction of the like the rest of the programs and generate more examples? So basically, like rather than changing the tokens, you're like, oh, actually, our program was only going to change the adjective, or we were going to create it based on this. But what we realized is that there's a spurious correlation that the word is, or whatever it might be, or some other thing is actually what's causing the model to behave this way, not the thing that you would have thought it was. So you could leverage that to basically create templates that are.
So great question. The question is basically, right now most of the examples created seem to be a little bit arbitrary, right?
Not my language.
Yeah, not your language. I paraphrase it. You're too polite to say that. But basically, is there a way to guide the generation of those examples using some knowledge we have about the model? Like, for example, the model is using some kind of artifacts, and then can we detect those artifacts and then particularly make edits on those artifacts so that it convey the message that this is an artifact to humans so that they would not believe the things that they were believing. We actually tried that a little bit in Polyjuice. There was a section in that paper that was saying, can it help improve the model understanding? And the way we tried to signal what parts of the sentence to change was through SHAP. So basically, we use SHAP to say, like, these are things that seem to be important, these are things that seem to be not important. But because SHAP, like, the way it perturbs things is not really natural, it creates this false sense to human, like, if, for example, in a sentiment analysis case, this is a good movie, if it highlights good, then it just make you think like the model is doing correct. But we try to create examples that would surprise you based on your current mental model. For example, we would tell you, like, if you change movie, which is supposedly not important, to book, the model just get negative. So it's like not really not using anything about that not important feature. Or if you change good to bad and it's still positive, it's like there will be edge cases that challenges your current belief. That particular section was trying to argue that the current explanation method needs more help, and counterfactual is one way to help that. But I think, like, that to generalize that idea a little bit, I do think, like, using it on artifacts or other, basically extend other detection methods so that it instantiates those findings into examples that people can read, actually will bump the understanding. Yes?
I have a clarification question.
Yeah.
So in the polyjuice, how do you define that this is a counterfactual of a given question? Like, because there are like various ways of like wording it, and like how do you establish that this particular wording is a counterfactual of a given question?
So yeah, the question is basically how do you know two examples are counterfactuals of each other? Is that?
Yeah, something like, yeah.
Right.
So for instance, like in the case of like removing an adjective, for example, yellow donuts, there could be various ways of like removing, of like perturbing it, like changing it with a different adjective, which can be of the same color or can be of something like big or small. Are these all counterfactuals?
Oh, yeah. Yeah. So in the definition of that polyjuice paper, they kind of are all kind of considered to be counterfactuals. Physically, we try to take this definition from psychology and philosophy and say like counterfactual is basically what could have happened. And so it doesn't really depend on, for example, it's like relevant to adversarial examples, but adversarial examples have some like particular like requirement on after the change, the ground truth answer should not change. Ground truth answer should not change, or it shouldn't matter to the human eyes, but then it should matter to the predictor. We don't really have those kind of requirements basically, but we try to measure like how far away you're perturbing from the original sentence based on just editing distance from the more like syntactic perspective. And if the like syntactic distance is lower than a threshold that I have to check again, then we kind of consider it counterfactual. It's like not too different that you wouldn't recognize they were from the same original sentence.
I'm wondering if you have used or created some more finer annotations. Like for the counting problem, if you tell the model, okay, these are the 3 yellow donuts, would that have to help the training? Like if the annotation contains the 3 yellow donuts, that is 30% out.
Great question. So the question is, can we use this can we add more information or metadata into the annotation? For example, in the yellow donut example, can we actually annotate on the image, these are the 3 yellow donuts? Does that information help to improve the model? I didn't try that, but there are some literature. I think one of them that I really like is called the bottleneck, the concept bottleneck. It's from Stanford. That paper is basically saying you can try to annotate different concepts or parts on your image and say, for example, this is a bird, this is the head, this is something. And that information, first you try to predict that particular concept in your image, and then it will help the final end task that you want to do. The biggest bottleneck of that particular work is basically the annotation of those information would be pretty hard to get, but there might be a way to backtrack, like if you have the attention, like if how many yellow donuts, how many yellowish donuts, if it's all focusing on that 3 donuts, maybe that overlapping attention can help you create some noisy concept information that you can use to add into your data set. It's an interesting thing that we can explore. I just never did that, but interesting. Maybe you first.
I was just about to add, for text EQA, state-of-the-art systems
Yeah.
have this extra downstream task where they try to predict where the answer is in addition to just predicting the answer.
Right.
And so the 3 donuts case, if we try to predict where the 3 donuts are,
Cool.
which helps.
Yeah. Great.
Prove that it helps even in pre-training. So if you try to predict where the answer is and not just predict the answer, it doesn't.
There you go.
One more. Okay, so these last 2, and then we can take a break.
Okay, cool.
Hi, this is really cool.
Mhm.
You talked about like expectations that the experts define, like if there's 2 orange tests, there should be more than 2 or more tasks in the image.
Yeah.
Have you done or have you seen any work on like encoding that expectation at training time? Like those questions were in the same batch.
Oh, yeah. The question is, so right now, most of the expectation in my work is used during the evaluation, so that you know kind of the model after you have trained, does that match with how you think the model should behave? Has there been any work that actually used that expectation during the training? The answer is yes. There is a work, I think, in ICCV or CVPR that tries to basically use this intuition of like the groups, some of the groups should be, examples that are really close to each other should be also treated as a group together in the objective function. If you ping me on Slack or something, I can send you that paper. And there's also another paper, also from Stanford, I think the same group, that is more like trying to, on the embedding space, is trying to say if two examples have the same label, then like their embedding should also be, like the attention on those two examples should be closer. But if two examples are in different label classes, then their embedding should, their attention should also be different. So it's trying to define the objective function and try to push away examples that might have artifacts. For example, like the wolf and the dog with the snow background thing. If like the a wolf image and the dog image both have the snow background, and if the attention is on the snow background, then they both look really similar to each other. That shouldn't be the case, and they try to punish it as at the embedding level. I can also send you that paper.
About changing as a way to deal with the wrong answer.
Yeah.
Would it make sense to look at changing incorrect answers as a way to explain the process behind that output?
Correct me if I didn't understand the question. Is the question about like can chaining help us do error analysis, basically explain like the errors that the model is making by saying like at certain step the model fail?
Well, if the answer was correct, actually, would it make sense to look at chaining as a way to build an explanation for the answer?
So the question is like, if we have the correct answer in the end, would it make sense to use the chain, basically chain of thoughts, as an explanation to provide to the human or explain the model behavior? That's a very interesting question. It's debatable. I think it may be from the user perspective, it's like comforting to know like the thing seemed to be working in a reasonable step. But I feel like large language models themselves are not super explainable, so it's always a little bit debatable to know like if anything it generates should be used as an explanation. But that's something we can debate later. Okay, I think that was the last question.
Yeah, so I think we'll share it one more time.